Okay, we're here to talk about constant power output and its effect on acceleration. And everything I'm going to talk about here, we need to understand the context is this. Linear motion, motion in a straight line, starting from rest and no friction. I know it's unrealistic to not have friction, but this is going to be complicated enough. We could always throw in friction later. If we plot the kinetic energy and the velocity of a 2 kilogram mass that starts at rest and accelerates at 1 meter per second squared without friction and linearly versus time, we get this. Now I used a 2 kilogram mass because kinetic energy is 1/2 mv squared. If I put a 2 here for m, then that falls out. I've got a 1, and kinetic energy can be directly related to velocity. But if I plot that data for the first 5 seconds, the velocity increases to 1 meter per second, 2 meters per second, 3 meters per second, 4 meters per second, 5 meters per second, etc. But the kinetic energy is a square function of that. So it's 1/2 mv squared. So the kinetic energy is at the first second 1, at 2 seconds it's 4, at 3 seconds 9, 16, 25, etc. And you could also write this equation in terms of v. Velocity is the square root of 2 times kinetic energy over m. Now, this is great. This is what you always see in the textbooks. This is the examples that's always given, but there's only one problem with this. This motion hardly ever exists, and not just because of friction. Accelerations are rarely constant. If you have something that's fairly dense, let's say baseball density or greater, and fairly aerodynamic, let's say baseball aerodynamics or better, and it's not falling very far, maybe dozens of meters, and not very fast, certainly less than tens of meters per second, then you would see this graph. But that's a really narrow set of acceleration data. Otherwise, you don't see constant accelerations, and not just because of friction and air friction, for example. An accelerating car doesn't have a constant acceleration, almost never. And you see problem after problem after problem. All the problems in the book have a car of some sort with a constant acceleration. But it doesn't happen. Very rarely does it happen. It's pretty common for something, though, to have a constant power output. Let's say a car pushes the accelerator all the way to the floor, and the engine produces maximum power, and you're trying to get data off of that. That's a very common situation in your life. But what that does is results in kinetic energy that increases linearly. When that happens, this velocity still follows the same square root relationship. So let's take the same 2 kilogram mass, but look at this time. The kinetic energy doesn't go up in a curve, a parabolic curve. Very commonly, if you're adding energy to something, power to something, and you're adding the power at a constant rate, the kinetic energy is going up to 4, 6, 8, 10 joules linearly. It's gaining the same amount of kinetic energy every second. That is because power is equal to work times time, or work divided by time. That's what you're doing. Now, if you plot this same relationship here, if you square the velocity, you get the kinetic energies on the first page. And that's what we're all used to seeing. But this just is a really rare situation. More common one is to have the kinetic energy increasing linearly, but the velocity is the square root of that. So these same two equations still hold. But rather than focusing on the first one, where we're always squaring the velocity to get KE, the more common scenario is to take the square root of a function of the kinetic energy to get the velocity. So if the kinetic energy is increasing by 2, 4, 6, 8, and 10 joules every second, it's going up by 2. The velocity is increasing as square root of 1, square root of 2, square root of 3, square root of 4. Square root of 2, square root of 4, square root of 6, square root of 8, square root of 10. So this first data point is square root of 2 function, square root of 4, square root of 6, square root of 8, square root of 10. This is the more common, much more common scenario that you would see as you're adding energy to something moving linearly. Okay, so let's take that same graph there this time, and let's look at the derivative of it. Take a little section of time, a very small increment of time, and see how much kinetic energy increases in that little increment of time. So what we've got is change in kinetic energy increasing slightly over the time interval increasing slightly. So you've got a little slope there for that. That's your derivative, basically. And you can do the same thing for velocity. But here's what you notice with kinetic energy. Since that's a straight line, that slope's the same all the way up, including that little interval of time that you're studying. But the slope of the change in velocity divided by the change in time, take a little increment of time, delta t, and you see how much the velocity increases over that. Basically on these you've got rise over run, rise over run. You've got a little slope there. But notice back at the beginning, the slope is greater than that. The slope back at the beginning is going something like, whoops, fairly steep, a little less steep, a little less steep, almost horizontal. You get the idea. That slope is not constant. So if I take this one, whoops, if I take that increment for just that one, that's that slope. Now, if I plot these slopes, I get a straight line for the power input. By the way, change in kinetic energy over time, that's power. If work is going all into kinetic energy and use power as work divided by time, then it's also kinetic energy divided by time. So the power slope remains the same, so we can plot the power the slope remaining the same, remaining the same, remaining the same as we go. But the acceleration gets less, the slope gets less and less and less the farther you get out. So the acceleration as we plot it gets less and less and less and less as time goes on. Okay, let's go back one screen. It turns out our delta Ke over delta T is power. It's also the slope. So basically we're taking the derivative, and when we plot that, we get the straight line. If we're adding power at a constant rate, like with an engine operating at maximum power, the power through time keeps a constant value. But when we take delta V over delta T, that value is acceleration, and it's the slope. And you're taking the derivative, and you're plotting it. But this time the slope gets less and less steep here. Less and less and less and less steep as we go out. And so when you plot it, you're getting decreasing values, less and less and less and less and less and less. So we get a surprising result that looks like this, where the longer you're adding power and the further you're going through time and distance, the less the acceleration is. But this is a very common outcome. Accelerations are only rarely constant. Now, this type of a result squares with the experience of riding in an accelerating car. If you're in a car and somebody smashes the accelerator to the floor, at first you feel the seat pushing into you, you feel a high acceleration. But the longer you go in time and distance, the less and less the seat pushes into you and lower your acceleration is. Now this also squares and agrees with the mechanical advantages of the gears changing in the transmission. As you're adding, the engine's adding power at a constant rate, you're adding, going to higher and higher gears, the mechanical advantage is less and less, and the acceleration becomes less and less because the torque is less and less. Now, another thing I can show you is that acceleration must decrease as power is increased, as power is added evenly and continually. The acceleration must decrease. I can show you that another way. Now, power is equal to work divided by time. If we reorganize the units, we end up with power equals force times velocity. Power is work divided by time. Work is force times distance divided by time. Notice distance divided by time is velocity. So right away, I've got force times velocity is power. If I want to rewrite the units for force, I've got newtons. Distance per second, or per time, I've got newtons times meters divided by seconds is the unit there. Newtons is kilograms times meter per second squared times this original meters per second is still there. If I reorganize that, my first kilograms times meter divided by second squared is force. Then my meters over seconds is velocity. So power is also equal to force times velocity. Now, if the power is at a constant rate, so P is a constant, and the velocity is going up as this car is going faster and faster and faster, in order for this number to be a constant as velocity goes up, force must decrease. And you don't think about that in the problems because they always give you a constant acceleration. And since the force must decrease with F equals ma, and the mass of the object, let's say, isn't changing, it's staying a constant. If the force goes down, it must be the case that the acceleration is also decreasing. So we've come up with another way to show this data. As the power is added constantly, the acceleration decreases and decreases and decreases as the object goes faster. Furthermore, assuming the motion starts from rest, and the velocity does increase, but the velocity does not increase linearly. As the acceleration drops off, the velocity increases become less and less. So as the acceleration drops, notice the steepness of the velocity curve gets less and less steep. And so that's the sum total of it.